Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 23, 2026, just yesterday. It introduces the VBVR dataset, a massive collection of over 1 million video clips designed to teach models spatiotemporal reasoning, making it about 1,000 times larger than existing alternatives. The paper is titled, "A Very Big Video Reasoning Suite." And as we'll see shortly, the scaling studies reveal some really striking emergent behaviors that could change how we approach video generation. You can find the 14 billion parameter model weights on Hugging Face. Plus, they have included usage examples to help you test this video reasoning suite right away. To understand the significance of this work, Figure 1 illustrates the sheer scale of the project compared to prior efforts. In the center, the massive circle represents the 2 million samples in the VBVR dataset, dwarfing the tiny blue dot that combines all 9 existing datasets. The surrounding grid displays examples of the 200 reasoning tasks, such as spatial mazes and physics simulations. Up in the top right, the line graph tracks improvement with more training data. Crucially, the pink line shows out-of-domain performance rising, which confirms the model is learning to generalize rather than just memorize. Finally, the radar chart on the bottom right shows their fine-tuned model, in red, outperforming proprietary giants like Sora 2 and VO 3.1 across all cognitive categories. Table 1 breaks down the specific numbers that drive this performance gap. If you scan the rows for existing benchmarks like Video Zero Shot or MMGR, you will see a lot of zeros in the video and training columns, because most prior efforts were just small test sets with practically no training data. In contrast, the bottom row highlights the VBVR dataset, which introduces over 1 million video clips and 1 million training examples. This massive volume is what finally allows researchers to train models on video reasoning rather than just evaluating them. To structure this learning process, Table 2 presents the 5 foundational faculties that categorize all 200 tasks in the suite. The first faculty, abstraction, focuses on finding hidden rules within observations to deduce logical results. Moving down the list, we see spatiality, which tests the model's intuition for 3-dimensional geometry and Euclidean space. Finally, the bottom row, transformation, is particularly important for video. It requires simulating spatiotemporal continuity, meaning the model must maintain a consistent internal world model as things move and change. So, Table 3 reveals the actual benchmark results, comparing human performance against both open source and proprietary models. The top row establishes the ceiling, where human evaluators achieve a near-perfect score of roughly 0.97. In the middle sections, we see that even leading proprietary models like Sora 2 and VO 3.1 struggle, managing scores of only 0.55 and 0.48 respectively. But the real story is in the bottom row. The fine-tuned versus BVR1 2.2 model leaps to 0.69. This represents a massive improvement over the base open-source models, proving that specialized reasoning data is key to bridging the gap between video generation and physical understanding. Now, you might wonder if these automated scores actually reflect real quality. This figure validates the evaluation method by plotting the automated benchmark scores on the vertical axis against human preference on the horizontal axis. On the left, the in-domain tasks show a strong correlation of about 0.93, meaning the metric tracks well with human eyes. On the right, the out-of-domain chart confirms this, with an even higher correlation of roughly 0.98, proving that these rule-based scores are a reliable proxy for human evaluation. Alright, with the evaluation method validated, Table 4 breaks down the scaling behavior as we increase the training set from 0 to 500,000 samples. In the top row, the base model, labeled 0K, starts with a low overall score of 0.37. As we add data, the in-domain average column shows massive improvement, climbing from 0.41 to a peak of 0.77. Crucially, the out-of-domain section on the right also rises to over 0.6, proving the model is genuinely learning to reason on unseen tasks. However, looking at the bottom rows, the scores stabilize after 200,000 samples, suggesting that data scale alone eventually hits a ceiling. Wrapping up, 2 things are clear. Massive data scaling unlocks emergent reasoning in video models, yet a persistent performance gap remains. This suggests that while dataset size is critical, we likely need new architectures to truly master physical dynamics. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.